Alright, let's consider polynomial functions. So a polynomial function can be written as f of x is equal to axn plus bxn minus 1 plus cxn minus 2 and so forth to some constant, let's say f. Okay? And basically you can understand that these are basically what we call power functions. And the first term here with the highest power is called the leading term. Now the leading term has the highest power, it's what's called the degree. So the degree is the highest power. And with the degree we can actually we can infer some type of behavior characteristics associated with the polynomial function in question, right? So technically if we had a degree of, let's say, 1, then the behavior of that function is going to look linear. Okay, so a linear equation, right, you would have seen it as y is equal to mx plus b. If there's a degree of 2, it's a quadratic equation, right? So a linear equation would kind of look like this. That's just one example of a linear equation. A quadratic equation is a parabola, right? It can look like this. This is one example of a quadratic equation, right? A degree of 3 is cubic. Excuse me. It's more of like a sigmoid type of function, right? This is a cubic equation, right? So I'm just going to write the common types of each polynomial function. Right, degree of 4 quartic, right, degree of 5 quintic, and you just keep going on and on. Okay, so the degree is the highest power on a polynomial function. These values, a, b, c, right, for instance, these are what we call coefficients. Now, the value where x is to the power of 0, right, the f value here indicated is a constant. Okay, so the first term with the highest power is called the leading term. Specifically, its coefficient, this a here, this a is called the leading coefficient. Okay, and what makes polynomial functions unique is that these guys actually have constant finite differences. So let's look at this notion of what a finite difference is. Okay, so what is a finite difference? Well, a finite difference in general is basically, I'm going to use FD to represent finite difference. Excuse me. It's the rate of change of y with respect to rate of change of x, right? So it's basically the slope equation, right? And say we had a point of values or a table of values such as this, and let's consider that this is essentially a function. Okay, so I'm just going to plot some values. Okay, and let's say that this is itself a function, and let's figure out the finite differences to show that this is a polynomial function in fact, right? So if we're looking at the finite differences, the first finite differences that I'm going to be looking at are called the first differences. Okay, so I'm going to call these the first differences. Okay, let's use lowercase fd for that. Excuse me. So the first finite differences are called the first differences, and you can notice here that the change in the x value is constant here. So we actually don't need to calculate it because we actually created a constant x value just for simplicity's sake. Okay, the difference here is -1 minus -8, which is 7, 0 minus -1, which is 1, 1 minus 0, which is 1, and 8 minus 1, which is 7. Okay, so these are our first differences. Okay, and you basically would divide it over 1, but it's going to give you the same number. Okay, now we stated that all polynomial functions have a constant set of finite differences, right? So all polynomial functions have a constant set of finite differences. So at one point, the finite differences will all be constant. Okay, and whatever finite differences are constant will also reflect the degree of the function. So we'll actually take a look at that through example. Like if the second finite differences are constant, it's a second degree function. If the third finite differences are constant, it's a third degree function. Now you can imagine here that the first finite differences are not constant. So what we do is we look at the next finite differences. So the second finite differences are called the second differences. Okay, so look at the second differences. You do 1 subtracted by 7, which is negative 6, 1 subtracted by 1, which is 0, and 7 subtracted by 1, which is 6. Okay, and then you can see that this is still not constant, so we look at our next set of finite differences, the third finite differences, and you can see 0 minus negative 6 is 6, and 6 minus 0 is 6. Okay, you can actually see that the third finite differences are constant, right? So because we have a set of finite differences that are constant, excuse me. So because we have a set of finite differences that are constant, then this implies that we do have a polynomial function. So this actually verifies that we have a polynomial function, right? So this indicates that we have a polynomial function. Well, this also tells us that because the third finite differences are constant, this is a function with a degree of 3. So as a result, it should have a cubic sort of behavior, right? So it should kind of resemble this S-shaped or sigmoidal curve, right? So this is a cubic function, it's a degree of 3, right? Well, actually knowing the finite differences and the degree of the function, we can actually determine the leading coefficient, right? So I'm going to show you guys how to find the leading coefficient. So the value of the finite differences here are 6, right? The value of our degree here is 3. As a result, we can understand that our cubic function f of x should be in the form of ax cubed plus bx squared plus cx to power 1 plus d, right? Because we're using this general template that I outlined out here. F of x is equal to axn plus bxn minus 1 plus cxn minus 2 and so forth, right? So we're using that template to kind of demonstrate that. So that's why I got this. And we know that this is a cubic function. We want to figure out, let's figure out the leading coefficient. How do I figure out this a value? Okay, I'm going to explain why this is really useful later on, but right now, how do we determine the a value? Well, in this case, there is an equation, right? The leading coefficient times the degree factorial is equal to the finite difference. Okay, so this is an equation that you might want to remember. It's really useful in terms of finding your leading coefficient. So this is the equation. So once again, the a here represents your leading coefficient. Excuse me. The n represents the degree, and the fd represents the finite differences. Okay, so if you wanted to solve for a is equal to the finite differences over the n factorial, right? So let's solve for a here, right? Now what does this factorial mean? Well, a factorial, it's usually used in counting principle, especially when we're looking at arranging a certain number of elements a certain number of ways, right? So it's a study called permutations. For simplicity's sake, we just need to memorize what it means. So for instance, if I have 5 factorial, this is like 5 times 3 times 2, 5 times 4 times 3 times 2 times 1. If I had 9 factorial, this is like 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. If I had 4 factorial, this is like 4 times 3 times 2 times 1. So you get the picture behind this, right? So our leading coefficient here, the finite difference value that was constant is 6, right? You want to make sure that it's the finite differences that are constant. Okay, specifically it's the value of the finite difference that are constant, right? A here is the finite difference, 6 over n factorial, which is 3 factorial, and 3 factorial is 3 times 2 times 1, which is 6 over 6, and a is equal to 1. So this tells us that our leading coefficient is no other than 1. So our function here, just from knowing that, our leading term here is x cubed. Okay, and to find the rest of your coefficients like b and c and your constant d, you need to actually plug in points to do that. Okay, but beyond that, we just figured out a way to figure out the leading coefficient. So once again, polynomial functions have constant finite differences. Whichever finite differences are constant will reflect the degree of the function. By knowing the degree of the function, we can figure out a general aspect of its shape. Okay? So now we'll consider some other properties of polynomial functions, specifically their behavior and their end behaviors. Alright, let's use finite differences to determine the type of polynomial function that can model each relationship. Okay, so Michelle earns $200 per week plus 5% of sales, right? And her sales are associated with her earnings, right? So sales are an independent variable, earnings are a dependent variable, and we can understand that earnings, I'm going to use E, let E of S represent earnings after S sales in dollars. Okay, and we want to figure out a relationship here. Okay, so they're asking us to model this as a polynomial function. We know that polynomial functions will have a constant finite difference. So for us to kind of figure out what the polynomial function is, let's figure out the constant finite differences. Okay, so we know that finite differences can be expressed as delta y over delta x, right? You notice that each difference here is by 500. Okay, so the delta x value will be constant, so delta x will always be 500, right? Let's figure out our finite differences, right? So I'm going to call this my first differences, and this is my first difference is 1, this is my first difference is 2, first difference is 3, right? First difference is 4. I think it'd be easier if I construct a table just to kind of show you guys this out, right? So let's just reconstruct this table just so we can make a clearer picture here, right? So this is sales, this is earnings as a function of sales, right? You have 0, we have 500, we have 1,000, we have 1,500, we have 2,000, right? And here is 200, 225, 250, 275, and 300. Okay, so let's take a look at our first differences, or our first finite differences. I'm going to subtract these two, so we get 225 minus 200 over 500. Okay, so in this case, we'll basically get 25 over 500, which basically will be, if you punch this out in your calculator, right, 25 divided by 500 is going to be, 25 divided by 500 is 0.05, right? So you're going to see that is going to be constant throughout, right? 0.05 and so forth, right? So 275 minus 250, let's get rid of this notion here, over 500 is equal to 25 over 500, so 0.05. So you can see that the first differences are constant, right? So the first differences are constant. And if the first differences are constant, well, we also know that the slope delta y over delta x is basically the slope of the function, or the rate of change of the function, right? But we can also refer this to how we discussed the finite differences in leading coefficient initially. We know that this is going to be a linear function because the first finite difference are constant. So I'm going to express this as E of s is equal to ms plus b instead of mx plus b. We're just using s as our independent variable. And you can understand that this guy here is our leading term. Okay, because it's going to have power of 1. This is going to be s to the power of 0, but we don't write it because it's 1, right? Now this is going to be our leading term, and we understand this notion that the leading coefficient times the degree factorial is equal to the finite difference. Right, so the leading coefficient is the finite difference over n factorial. In this case, the first finite differences are constant, so it's going to be a degree of 1, right? N is 1. The finite differences here are 0.05. So this a value here is 0.05, and that leading coefficient is associated. So because we said that this is our leading term, right? This whole thing is our leading term. This is your degree. This is your independent variable, we're using s instead of x. And specifically, m here is your leading coefficient. So now we have the value of our leading coefficient, which is basically 0.05. Or what you could do is you could use the slope formula, and you can see that gives you the same answer because we found out what our slope is, and this is basically our slope, right? Our slope is 0.05 because we know that this is basically delta y over delta x, right? This is delta y, this is delta x. Right, so technically the equation here is going to be, I'm just going to change colors here so we can kind of distinguish which steps we followed. Y is equal to 0.05x plus b, and b here is your y-intercept or your initial point, right? And in this case, e of s is equal to 0.05s plus b. We know that e of 0 is equal to 200, and e of 0 here is equal to, because we're using this point basically, right? E of 0 here is equal to 0.05 times 0 plus b is equal to 200, so therefore b is equal to 200, right? So the equation here to represent Michelle's earnings, therefore e of s is equal to 0.05s plus 200 is an equation to represent Michelle's weekly earnings. Okay, so this is a good way to kind of represent Michelle's weekly earnings, right? So you wanted to kind of identify that this was weekly earnings initially, right? So just try to be as specific as possible, right? So that's the idea behind how we can actually use this notion to create a polynomial function to model different scenarios, like real-world examples. Okay, let's demonstrate that the following is a polynomial function and infer its behavior. Then we want to determine the leading term. So we know that polynomial functions have a constant finite difference. Right, so let's start by determining the finite differences. And let's start with the first finite differences in red. Right, so you can notice that the change in, we know that finite differences is basically delta y over delta x, and we can notice that delta x here is always 1, so we just have to divide everything by 1. So we're just really looking at delta y, right? So this is positive 1, this is positive 1, right? 2 minus 1 is 1, 3 minus 2 is 1, 4 minus 3 is 1, and so forth. Okay, so let's look at our first finite difference. I'm going to do that in red. 4 minus 9 is negative 5, 1 minus 4 is negative 3, 0 minus 1 is negative 1, 1 minus 0 is 1, sorry, 4 minus 1 is 3, and 9 minus 4 is 5. Okay, so that's our first finite difference. You can see that the first finite differences, or the first differences, are not constant. Let's take a look at our second finite differences. So our second finite difference is negative 3 minus 5, right? So in this case, it's going to give us 2, negative 1 minus negative 3, which is 2, 1 minus negative 1, which is 2, 3 minus 1 is 2, and so forth. So you can notice that our second finite differences are constant, and because our finite differences are constant, this is a polynomial function. Because the second finite differences are constant, we can understand that the polynomial function will have a degree of 2. Okay, so therefore it's a quadratic function. So because it's a quadratic function, right, y should be equal to ax squared plus bx plus c. Okay, now we want to determine the leading term, right? So the leading term here is ax squared. The last thing we need to do here is we need to find the leading coefficient. Let's solve for a. This is your leading coefficient, right? And a times n factorial is equal to the finite differences. We can use this equation. A is equal to the finite differences over n factorial, and the finite differences here are basically equal to 2. I'm going to divide this by the degree factorial, which is 2 factorial, which is 2 over 2 times 1, which is 1, right? So in this case, a is equal to 1, so our leading term here is x squared, right? So that's our leading term, and we've proven that it's a polynomial function because our second Okay, recall that we mentioned that polynomial functions have constant finite differences, and we can express a polynomial function in the form of f of x is equal to axn plus bxn minus 1 plus cxn minus 2 plus, and I'll just keep going to some coefficient, or sorry, to some constant e, all right? So this is the general template of a polynomial function, and we stated that they had constant finite differences, and whatever those finite differences, whichever finite differences were constant, would tell us the degree of the function. Furthermore, we also said that the degree of the function would tell us the behavior of the function, right? And we made this chart where the degree and the behavior were related. If the degree is 1, we have a linear function. If the degree is 2, we have a quadratic function. If the degree is 3, we have a cubic function. If the degree is 4, we have a quartic function, and if the degree is 5, is quintic. And you can keep going with this, but for the most part, we'll just mainly be looking at the first 5 degrees, if anything. Okay. We can understand that knowing the degree of the function can help us to understand some of its behavior, specifically its sketch of its graph, right? But we want to create a general statement regarding the properties of all polynomial functions, right? So that way we're not just restricted to a degree of 5, right? Remember that degree is the highest power on a polynomial function. So before we start with our description of each of these polynomial functions, let's look at some general rules here, right? So let's take a look at two types of degree functions. So degree is the highest power on a polynomial function. And the two types of polynomial functions in terms of the degree can be even degree polynomial functions. So even degree polynomial functions have, well, basically even degrees, right? So their degree is an even number, right? And we'll also look at odd degree polynomial functions, right? And basically the degree is an odd number. Okay, so like for instance, if we had a function that looks like this, let's call this f of x is equal to x cubed minus 5x plus 4, we can understand that the degree here is 3. It's the highest power on the function, and this essentially would be an odd degree polynomial function. Okay, and if we had something like this, g of x is equal to x squared plus 3x to the power 4 minus 5x cubed, well, our degree here is 4 because that's the highest power on the independent variable, and this would be an even degree polynomial function. Okay, now you're probably wondering, okay, why do we need to classify even and odd degrees? Well, it actually tells us a little bit about the behavior, specifically the end behavior. Now, what is the end behavior of a function? Okay, well, an end behavior of a function right? The end behavior of a function is basically the value of y when x approaches positive or negative infinity. Okay, so I think the best way is to draw this out, right? This is our function, okay, and this is a linear function, right? And if this is our function, this is the x-axis, this is the y-axis, right? If we go towards this arrow here, this is positive infinity for x. If we go to this arrow here, it's negative infinity for x, right? If I go, as x approaches positive infinity, look what happens to y. You're going to keep extending this line outwards, and y will also approach positive infinity. So as x approaches positive infinity, y will also approach positive infinity, okay? So how we can look at this is the end behavior of y when x approaches infinity, right? So the end behavior for y when x approaches infinity is positive infinity, right? So what we can do is we can look at the direction of the arrowheads, right? The arrowhead just means that the function is continuous, so it's not restricted within a certain interval. Let's take a look at the other scenario as we go down this way. As x approaches negative infinity, right, you can see that y is going to go down, right? This is positive infinity for y, this is negative infinity for y. And as x approaches negative infinity, y will approach negative infinity as well. Okay? Now, you can understand that when x approaches positive infinity, y approaches positive infinity. When x approaches negative infinity, y approaches negative infinity. These are what we call the end behaviors. Okay, you can see that, and this is what we call opposite end behaviors. If the two end behaviors are opposite, they don't point in the same direction, we call these opposite end behaviors. Okay, let's take a look at another example where we have similar end behaviors. All right, let's consider this function. This is actually a quadratic function, and you can imagine that because it's shaped as a parabola, and you can imagine here that this is x and this is y. This is positive infinity towards x, negative infinity of x, positive infinity of y, and negative infinity of y. As I go towards positive infinity, as x approaches positive infinity, look what happens to y. Y is basically increasing this way if you follow the trace, and y is approaching positive infinity as well. Okay. Now if x approaches the opposite direction, negative infinity, you can see that y is also going up this way, and you can see that y also approaches positive infinity. Okay. So in this case, because the two end behaviors are in the same direction, right, therefore they have same or similar end behaviors. Okay, so the previous example, we looked at opposite end behaviors here, right, these guys, this was an opposite end behavior, right, but here we have similar end behaviors. Okay, and another thing you can note here is that this was a linear function, right? So this was an x to the power 1. The degree was 1, so this is actually an odd degree function, right? Versus this was a quadratic, so this was an x to the power 2 function, right? And as a result, this is an even degree function. Well, this is actually a more universal rule, right? And what I want you to really understand here is that all even degree functions have similar end behaviors. They have the same end behaviors. Okay, so all even degree functions have similar end behaviors, whereas all odd degree functions have opposite end behaviors. Okay, so even degree functions have similar end behaviors, odd degree functions have opposite end behaviors. Now this is really important, right? So this will give us a general rule for basically any kind of degree polynomial function that you encounter. Now these rules are also dependent on the leading coefficient, specifically if the leading coefficient is negative, right? So A, we said, is the leading coefficient. Excuse me. And now let's take a look at when A is equal to, what we need to do is we need to look at the sign of the leading coefficient. A can be positive or A can be negative. Okay? Now if you tie this in with n, right, the degree, there's going to be specific characteristics that you want to look at. Now if n is equal to an even number, and n is basically the degree of the function, right, then this is an even degree polynomial function. Okay. However, if A is positive, right, if A is positive, then what you're going to see here is that the end behaviors are going to be the same because all even degree functions have the same end behavior. I'm going to use EB for end behavior actually. The end behaviors will be the same, but they'll always point to positive infinity. So because they're always pointing to positive infinity, if you have a positive even degree polynomial function, Okay, here is our quartic function. A positive even degree polynomial function will have the same end behaviors. Both of them will be positive infinity, and you'd actually find the end behaviors in quadrants 1 and quadrants 2. So this is called a positive even degree function. Okay. Now if a is less than 0 and n is basically an even number, right, the end behavior will still be the same, but it'll both be negative infinity, right? So basically you'll have a negative even degree function, and what it would look like, here's an example of a negative even degree function. Right, the end behaviors would be in quadrants 3 and quadrants 4. Okay, so make sure you can note this, and you have to memorize this out because this is true for all positive and negative even degree functions. Okay, let's take a look at odd degree functions. Okay, let's say if n is an odd degree. If a is greater than 0, then what we're going to get here is a positive odd degree function. So here's an example of a positive odd degree function, right? So you can notice here that odd degree functions, the end behavior you'd have opposite, and specifically the two end behaviors will be found in quadrants 3 to quadrants 1. So start in quadrant 3 and end up in quadrant 1. Okay, and this is true for all positive odd degree functions. So this is a positive odd degree function. Okay, and if you have a negative degree, like if a is less than 0, right, and you still have an odd degree, right, then basically what your function will look like right, this is quadrants, well, this was 1 and 3, right? This is quadrants 2 and 4. So in a negative odd degree function, the end behaviors are still going to be opposite, right? You can see that the end behaviors here, this is positive infinity, this is negative infinity, right? So the end behaviors are still opposite, but this time they're basically going from quadrants 2 to quadrants 4, right? So this is a negative odd degree function. Okay, so it's a negative odd degree function, and it's going from quadrants 2 to 4, right? So this is true for all positive and negative odd degree functions, right? So to recap, to summarize, right, the degree can tell us a few things about the characteristics of functions, right? And if the degree is an even degree function, right, you're going to have the same end behaviors, right? But if it's a positive even degree function, then you're going to have the end behaviors in quadrants 1 and quadrants 2. If it's a negative even degree function, you will have the end behaviors in quadrants 3 and quadrants 4. Okay. Now, if n is an odd degree function, odd degree polynomial function will have opposite end behaviors. If it's a positive odd degree function, we'll find the end behaviors in quadrants 3 and quadrants 1. And if it's a negative odd degree function, we'll find the end behaviors in quadrants 2 and quadrants 4. Okay, so keep this in mind, and I'll show you guys some questions later on to kind of illustrate some of these. Alright, for each of the following graphs, decide if A, the function has an even or odd degree, B, the leading coefficient is positive or negative. Okay, so for part 1, if the function has an even or odd degree, well, we can tell here that for part 1, the end behaviors are the same, right? And because the end behaviors are the same, this is going to be an even degree function. And this is for part A. For part B, right, the leading coefficient is positive or negative. Because the n behaviors are found in quadrant 3 and 4, then it's just going to be negative, right? So this is going to be negative, right? The leading coefficient will be negative. Part 2, the function has an even or odd degree. Well, in this case, we have opposite n behaviors. This one goes to positive infinity. This goes to negative infinity. So because you have opposite n behaviors, this is going to be an odd degree function. And part B here, the leading coefficient is positive or negative. Well, because you find this in quadrants, this is quadrant 2 and quadrant 4, right? This is going to basically have an even sorry, did I say even? I meant negative. This is going to have a negative leading coefficient, right? So if it's a negative leading coefficient, you're going to find the n behaviors in quadrants 2 and 4 if it's an odd degree function, right? And in question 5 here, and I know it doesn't go in order. I just kind of took these questions from the textbook, but you can see that once again there are opposite n behaviors, and this is basically for part 5 here. Part A, basically this should be an odd degree function, and for part B here, because you're going to find the n behaviors in quadrants 2 and quadrants 4, then you should expect it to have a negative leading coefficient. Okay, so a few rules just kind of to summarize this, just in case if you need a recap, right? We know that even degree functions have similar n behaviors. Okay, if the leading coefficient is positive, then we're going to find the n behaviors in quadrants 1 and quadrants 2. If the leading coefficient is negative, we're going to find the n behaviors in quadrants 3 and quadrants 4, right? For odd degree functions, we're going to have opposite n behaviors. We're going to have opposite n behaviors. If you have opposite n behaviors, if a is greater than 0, we're going to basically have the n behaviors that will stem from quadrants 3. I'm just going to clear that one up a little bit. But it's going to stem from quadrants 3 to quadrants 1. And if you have negative n behaviors, it's going to stem from quadrants 2 to quadrants 4. Okay, so keep that in mind, basically, right? So it's really important to kind of understand these characteristics because it will help you to sketch the polynomial functions a lot more clearer. Alright, let's describe the n behavior of each polynomial function using the degree and the leading coefficient. Start with part A, right? So you can see that the degree, the highest power here, degree here is a 2, right? So this is an even degree function, right? Particularly, well, specifically, this is a quadratic function. If it's an even degree function, we can understand that this is going to have similar n behaviors. Now we can notice here that the leading coefficient, a is equal to 2, a is greater than 0, and as a result we have a positive, should mention a is greater than 0, so this is a positive even degree function. So if it's a positive even degree function, you'll have similar n behaviors, and the n behaviors should be in quadrants 1 and quadrants 2. Okay, now in part B here, the degree of the function is 3. Okay, so this is thereby a cubic function, and a cubic function is going to be an odd degree function. Okay, so because it's an odd degree function, it's going to have opposite n behaviors. Because it has opposite n behaviors, right, it's going to be found in opposing quadrants, right? Now we can also notice here that the leading coefficient is negative 3, because the leading term here is negative 3x cubed, right? The leading term in part A was 2x squared, right? This is the leading term. Right, so the leading term here is negative 3, and in this case, the a value is less than 0, and in this case, we should have a negative odd degree function. Right, so the n behavior in a negative odd degree function should be in quadrants 2 and quadrants 4. So what that will look like is, it should be somewhere up here and somewhere up here, somewhere down there, right? So positive infinity, negative infinity, and for the first scenario, right, you should see the end behaviors in the same direction, right? So that's the idea, really. Okay, so now we're going to consider even and odd functions. Okay, now this isn't directly similar to even degree and odd degree functions, right? Because you can actually apply even and odd functions to functions outside polynomials. But these guys indicate there is a relationship between even and odd degree functions, which we'll talk about, but these guys represent or demonstrate lines of symmetry. Okay, so an even function, by definition, they contain a line of symmetry about the y-axis. Okay, so an example of an even function, I think the most common type of even function is a quadratic function, right? So this is my quadratic function. You can notice here that about the y-axis, this should be generally symmetrical. So I know I didn't draw this to scale, but this is y is equal to x squared. And along the y-axis here, I'm just going to highlight the y-axis. Right, along the y-axis, this line should create a line of symmetry. Okay, so all even functions have a line of symmetry about the y-axis, right? And I did highlight an even degree polynomial function, which I will talk about in a little bit. But let's take a look at odd functions. And odd functions, they contain a rotational line of symmetry about the origin. So what does a rotational line of symmetry mean? Well, if this is our function. Okay, let's say this is y is equal to x cubed. This is our function. A rotational line of symmetry about the origin means that there is this line that if you rotate it, right, you can understand that this is basically a plane. So imagine that this line is a plane, and these two halves are symmetrical, right? They're mirror images of each other, right? But if I rotate this line, and let's say that I move the line, let's say it's here now, right? And you can see that this half and this half are still mirror images, right? So if you keep rotating the line, right? If you keep rotating the line, you should see that you should still keep getting lines of symmetry. Okay, so that's what a rotational line of symmetry is, right? And you can test this algebraically. All even functions will satisfy this notation: f of negative x is equal to positive f of x. Okay, so this is something that you want to memorize. Okay, and this is how you can show a function is an even function algebraically. If you wanted to show an odd function algebraically, all odd functions will satisfy f of negative x is equal to negative f of x. Okay, so this is the tenet for all odd functions. Okay, so I'm going to demonstrate this using an example. Like, for instance, if the function f of x is equal to x cubed plus 5x, right? You want to test to see if it's an even function or odd function. Another quick way we can tell is if we're considering polynomial functions. What you need to remember is that all even functions are even degree polynomial functions, and vice versa, that all odd functions are odd degree polynomial functions. Okay, just having these rules in the back of our mind, we can understand that we know that this all even functions have to be even degree polynomial functions. This is not an even degree polynomial function, so we would do the test for odd functions, right? So the test for an odd function here is f of negative x should equal negative f of x. Well, I'm going to first test out f of negative x here. F of negative x is I plug in negative x for wherever I see x. In this case, negative x cubed is negative x cubed, right? Because if you multiply negative x by itself 3 times, there should be a negative on the outside, minus 5x. Now the next thing I want to test here is negative f of x, which is basically negative applied to the outside of this function, negative x cubed plus 5x, which is basically negative x cubed minus 5x. You can see that these two here, right, these two here are the same, right? So therefore you can say that f of negative x is equal to negative f of x, and f of x is an odd function. Okay, so that's the test algebraically, right? Let's take a look at another example. Now let's consider f of x is equal to 2x to the power 4 minus x squared. I'm going to do f of negative x here, right? And in this case you have 2 to the power negative x to the power 4 minus negative x squared. Now you can understand that the degree here is 4, so this is an even degree polynomial function, right? So this is an even degree polynomial function, so because it's an even degree polynomial function, we only understand that even functions have to be even degree polynomial functions. So I'm going to first test out f of negative x, but we recall that an even function f of negative x should be equal to f of x. Okay, so this was the tenet for an even function. So f of negative x here is 2 negative x to the power 4 here is x to the power 4 minus negative x squared is x squared, right? And you can see that f of negative x here is equal to f of x. Right, so therefore f of x is an even function. Okay. Now there are cases where both of those tenets don't exist, right? If f of negative x is not equal to f of x, or f of negative x is not equal to negative f of x, then we say that the function is neither. And neither just means that it does not contain a line of symmetry. Okay, so it doesn't contain a line of symmetry is the idea. Okay, an example of this, let's say f of x is equal to 5x cubed plus 2x squared minus 4x plus 1, right? And you would think that because the degree here is 3, you think this is an odd degree polynomial function, right? It's an odd degree polynomial function, so you could do the test. If you want to test to see if it's an odd function, f of negative x should equal negative f of x, right? If I plug in f of negative x here, you get 5 times negative x cubed plus 2 times negative x squared minus 4 times negative x plus 1. And you can see here that you get negative x cubed is negative x cubed, minus 5 times negative x cubed plus 2 times x squared, because the negatives would cancel out, plus 4x plus 1. And negative f of x here is basically negative 5x cubed plus 2x squared minus 4x plus 1. And if I expand this guy out, you get negative 5x cubed minus 2x squared plus 4x minus 1. And you can notice here that negative f of x, right, therefore f of negative x is not equal to negative f of x, right? And this was the test for an odd function. We can see here that, right, this would not be an even function because it doesn't have an even degree, right? So this is neither. So it doesn't have a line of symmetry is the idea. Okay, so even and odd functions are just associated with symmetry. In the case of polynomial functions, however, all even functions have even degrees, and all odd functions have odd degrees, right? However, that is not to say that all odd degree functions are odd functions, and not all even degree functions are even functions. So we saw that here, right? This was an odd degree function, but not an odd function, right? So although even functions all have even degrees in terms of polynomials, and odd functions have odd degrees in terms of polynomials, the opposite isn't true, right? That odd degree functions aren't always odd functions, and even degree functions are not always even functions, right? So that's also a very important characteristic to understand as well. All right, which of the following graphs represents an even function, right? So for question 13, we know that even functions, they have a line of symmetry along the y-axis, line of symmetry along y-axis. So the y-axis acts as a symmetrical plane, right, in an axis of symmetry, and they also, algebraically, they should also fulfill f of negative x is equal to f of x. However, we aren't given any algebraic statement, so we just have to purely demonstrate this through display, right? So we have to kind of just inspect it. Now, in this case, this doesn't seem like there's a line of symmetry along the y-axis, so it can't be A. There is a line of symmetry here, right? If this is the y-axis, it looks like a line of symmetry, so this would work. There wouldn't be a line of symmetry along the y-axis here, so it can't be B. And it doesn't seem like there is a line of symmetry here because of the fact that they are rotated, right? So the best case answer here would be C. Now let's take a look at number 14. Which of the following represents the odd function? Well, odd functions, remember that even and odd functions are associated with symmetry, so they're not just restricted to polynomial functions, right? And there's basically a rotational line of symmetry along the origin. So what that means is there's a line of symmetry along the origin, but also that the object or the shape of the graph is rotated, right? So technically, if I could create a rotational line of symmetry, I'm going to put a line of symmetry through the origin, and you can rotate this through the origin anyway, but you can notice here that there is no rotational line of symmetry between this half and this half, right? So it can't be A, right? Let's take a look at C, right? In this case, if I do a line through the origin, this is not a rotational line of symmetry because this half is not symmetrical to this half, right? So it can't be C. There also is no rotational line of symmetry here because then this half and this half aren't even symmetrical, can't be B. But you can see that D here has a rotational line of symmetry because this half and this half are mirror images, but they're just rotated, right? So it's going to be D in this case. Okay. Odd functions, they will have a rotational line of symmetry, and also algebraically, f of negative x should be equal to negative f of x. Right. Once again, odd functions are associated with symmetry, so they have to satisfy this. They're not just restricted to polynomial degrees, right? So that's the idea regarding symmetry. Alright, describe the function f of x is equal to negative 4x to the power 4 plus 3x squared minus 15x plus 5 is an even or odd or neither. What does this imply? Okay, so first of all, we can notice here that the degree of this function is 4. So this is an even degree function. So we made the statement that even functions have to have even degrees, right? So off the bat we can tell it's not an odd function, right? So because it's not an odd function, we just have to do the test for an even function. An even function just means that it satisfies this equation: f of negative x is equal to f of x, and all even functions have a line of symmetry, contain a line of symmetry along the y-axis. Okay, so what that means is that along the y-axis, it's just going to create a plane. So it's going to kind of look like this. So this is your graph, right? And you had like, you know, say this is your trace, right? If this creates a line of symmetry, didn't draw that out too well, between the two halves, right? Maybe if I just let's see if I could draw that a little bit better, right? So if this creates a line of symmetry between the two halves, then it's an even function, and the line of symmetry has to be along the y-axis. Excuse me. Okay, so this is the algebraic test to show that it's an even function. So let's test that out, right? So in this case, let's just use a different color for this. But in this case, let's do f of negative x. So we get negative 4 negative x to the power 4 plus 3 times negative x squared minus 15 times negative x plus 5. This is negative 4 x to the power 4 plus 3 times x squared plus 15x plus 5. And you can notice here that f of negative x is not equal to f of x because of the fact that the third term, this is positive 15x versus negative 15x, right? So because this is not an even function, and we know that odd functions have to have an odd degree, then we just simply say that therefore the function f of x, therefore f of x is neither an even or odd function, right, and is not symmetrical. Right? There is no line of symmetry that encompasses the function, right? Recall that for an odd function, there's going to be a rotational line of symmetry, so that what that would look like, right? This is your graph, right, and this is your odd function. There's a rotational line of symmetry along the origin, so what that means is that you could draw a line through the you can draw a line through the origin. You draw a line through the origin, and both of these ends here would be rotational lines of symmetry, right? So you can do that any sort of way, right? And basically these would be mirror images, but they would be symmetrical, right? So this is basically an odd function characteristic. This is an even function characteristic, and even and odd functions just have to do with symmetry. So the test for an odd function was f of negative x is equal to negative f of x, but it doesn't pertain to this scenario because it's an even degree. So we talked about how by knowing the degree of a polynomial function, right, and remember that polynomial functions are in the form of axn plus bxn minus 1 plus cxn minus 2 plus, and let's just keep going, let's say to e. N is the degree of the polynomial, right, and the degree is the highest power of the polynomial function, right, and a is the leading coefficient, and ax to the power n is your leading term. Now we said that by knowing the degree of the polynomial function, we can understand the behavior of the function as well as the end behavior. We said that even degree polynomial functions have similar end behaviors, and odd degree polynomial functions have opposite end behaviors. We also looked at variations of a positive and negative even odd degree polynomial function and how those end behaviors were different, which quadrants they would end up in, right? Now, using the degree, we can also figure out how many extrema or maximum and minimum points that can exist in a function, right? And this is what we call a turning point. A turning point or a turn are basically points of extrema, and they include maximum, minimum points. They also include points of inflection. Okay, so a turning point can be a point of inflection as well as a point of extrema. Now, what are points of inflection? Okay, I use POI for points of inflection and POE for points of extrema. Okay, well, we stated that points of extrema are maximum or minimum points, right? So if the curve ends up here and then this is a maximum, right? This is a point of extrema, so this is a max. Right? In another case, if the curve is concave down, this is a point of extrema, and this is a minimum point. Okay? A point of inflection is where you have a change in concavity. So for instance, if the curve here is concave down and it goes concave up, so this is a point of inflection, right? So this portion here is concave down, this portion here is concave up, right? Or another case, we have a concave up portion, and then the curve basically becomes concave down here. Okay, and this is another point of inflection. Okay, so all of these things are examples of turning points. I'm just going to look at turning points as turns, right? So we're going to call them turns, and this is really useful because we can use the degree to figure out how many turns you would possibly find in a function, right? And the maximum number of turns a function will have, I'm going to use t to represent turns, is 1 less than the degree. Okay, so put another way, n minus 1 should be equal to t, right? So the maximum number of turns that any function will have here is always n minus 1. Okay, so this is really useful, right? Because if we have a degree of 1, right? If we have a cubic function, right? So the degree here is, sorry, a degree of 3, not a degree of 1. A degree of 3, we should expect a maximum of 2 turns. Okay, so an example of 2 turns, an example of a cubic function, something that kind of looks like this, right? You can imagine that there is a turn, or there's a maximum here, and then there's a minimum here. Okay, so there's a turn here and a turn here. Okay, so that is an example of a turn, right? So there's 2 turns here, which is consistent with our notion that the turn here is the degree minus 1, so there's 2. Right, so that's really the idea, right? So this is a really useful notion to kind of understand. Furthermore, these turns or points of inflection are going to be usually located in between the x-intercepts. Okay, so for instance, say this is your graph. Okay, let's say that there is a y-intercept located here. Right, you can notice here that this type of function, right, that's opposite end behaviors, right, negative infinity to positive infinity, right? So this tells us, and we know that the end behaviors are extending from quadrants 3 to quadrants 1, right? So this is basically going to be a positive odd degree polynomial function. Another characteristic that we can understand here is there should be 2 turns, right? So one of the turns I showed, there's a minimum here at the y-intercept, and there should be a maximum here. So there's a maximum here, there's a minimum here. So potentially this is a cubic function, right? Because we can understand that the turns is the degree minus 1, so the degree here is turns plus 1. So because there is 2 turns, right, the degree should be 3. Okay, so it's really useful to kind of understand this. But specifically, these are 2 examples of points of extrema. Now let's say we knew the x-intercepts. Okay, now we know what the minimum point here is, but say we knew these 2 x-intercepts. Let's call these points A and point B. Okay, so the intercepts are A and 0, right? And the other intercept is B and 0, right? And you can imagine that these are negative, right? It's not too important, right? A is a negative number, B is a negative number, right? So A and B are both less than 0, right? Now, the idea here is that there is a maximum point located here, and the maximum point, or this point of extrema, will always be the midpoint, right? The x value of the maximum point is always the midpoint of the x-intercept. So the x value of the turning point, we'll use turning point to represent, because it can be used for minimum points as well. The x value of the turning point is basically the midpoint of the two x-intercepts. So you can think about it as a plus b divided by 2. Okay, and if you wanted to figure out the y value of the turning point, which is the maximum point in this case, right, the y value of the turning point is basically f of a plus b over 2, or you can just plug in f of the x value. You plug in the x value of the turning point into the function to find the y value, just like how you're used to doing it, right? So this is a really useful idea to kind of understand, right? Now, we need to also consider the domain and range of these polynomial functions. Now, we know that this is a positive odd degree polynomial function, but you can understand that the n behaviors here, positive infinity, negative infinity, they'll span the whole range, right? They'll span the whole range of the Cartesian plane, right? So because they'll span the whole range of the Cartesian plane on the y-axis as well as the x-axis, the domain for a positive odd degree or an odd degree polynomial function and you can actually memorize this, but it's good to understand it. The domain and range for all odd degree polynomial functions are going to be constant. X can belong to all real numbers because there is no restriction for the domain, and the range here, y can belong to all real numbers. So because there is no restriction for the range, specifically, right, all of these maximum and minimum points are not absolute. And absolute means that they will restrict the range, right? These maximum and minimum points are what we call local maximum and minimum points. And it's because these maximum and minimum points don't restrict the range of the function, right? So these are all examples of local maximum and minimum points. So odd degree polynomial functions will only contain local maximum and minimum points. Now, in some cases, you will have some questions will mention absolute maximum and minimum points, but that's only within a given interval. Like if you have a given interval, restricted intervals can include absolute max and minimum points, right? So if you have a restricted interval, you can have absolute max and minimum points, but a general domain where x belongs to a set of all real numbers, so a free floating domain is like what I like to call it. In that sense, you would only have local maximum and minimum points. Okay. However, if you're looking at an even degree function, okay, let's just draw that here. Okay, so if you're looking at an even degree function, and you can imagine that this is even degree because both of the n behaviors are the same. They're in quadrants 1 and 2. So this is an example of a positive even degree function, right? If you're looking at even degree function, you can note here that this guy here has 3 terms, right? So if it has 3 terms, then the degree of the function here should be 4. Okay, so this is an example of a quartic function. It's a degree of 4, right? And you can also see there that there are 3 different points of extrema. Okay, so I'm specifically just looking at the y-axis, but you do want to include these points of extrema, right? So let's say this is -2, and this is like 4, and this is like 1 and 6. This isn't drawn to scale, guys, so just bear with me here. This is negative 2 and 4. This is 1 and 6. And then this is like, let's do 3 and negative 6. Okay? You can imagine here that the domain will encompass all points. Okay, the domain actually will encompass all points because there is no restriction on the x values. It just ranges the entire span of the x-axis. The range, on the other hand, is limited. There is a restriction, and the restriction here, y belongs to all real numbers, but the lowest point that the y value can touch is greater or equal to negative 6, right? So this point here, the 3 and negative 6, is what we call the absolute minimum because of the fact that it restricts the range, right? Restricts the range. However, we can also notice another minimum located here at the negative 2 and 4 mark. Negative 2 and 4 is another minimum, but this one here is called a local minimum. Okay, so you can have multiple minimums and maximum, multiple minima and maxima in a function, right? But there's only going to be one absolute minima or maxima for each scenario, right? So this is the local minima, and because we had an absolute, so the absolute will only restrict the range, and then this here would be the local maxima, right? Or the local maximum at 1 and 6. So 1 and 6 represents the local maximum. Okay, so this is really important to understand, right? That the terms is always 1. The maximum number of terms a function can have is 1 minus the degree, right? And we'll only have local extrema in odd degree functions, and you can have local and absolute extrema in even degree functions. Okay, so with that being said, let's do some questions regarding characteristics of polynomials. Alright, using n behaviors, turning points and zeros to match each polynomial equation with the most likely graph below and explain. Alright, so we want to match each of these equations with a potential sketch. Now, I'm just going to write some characteristics for each of them. So part A here, for this function, y is equal to 2x cubed minus 4x squared plus 3x plus 2. This is an odd degree function, right? And it's also positive, so it's a positive odd degree function, so we should say that the n behaviors should be found in quadrants 3 and quadrants 1, right? So it's a positive odd degree function because the leading coefficient here is 2. And this tells us that we should also have opposite n behaviors. And furthermore, we should also see turns. You should always see n minus 1. So in this case, you should see a maximum of 2 turns. Okay, so let's take a look at part B. I'm just going to write some characteristics of each, and then we'll match it up with the original graphs, right? So this is, we can see that the degree here is 4, n is 4, so this is a negative even degree function. So if it's a negative even degree function, the n behaviors here should be found in quadrants 3 and quadrants 4. And the number of turns you should expect here in maximum is basically 3. Okay, let's take a look at part C. So part C here, we're looking at y is equal to x squared plus 3x minus 5, right? So the degree here, n is equal to 2, it's a quadratic, so the number of turns here, you should only have 1 turn, right? And this is also a positive even degree function. So if it's a positive even degree function, the n behavior should be found in quadrants 1 and quadrants 2. Okay, part D. We have y is equal to x to the power 4 minus x cubed minus 4x squared plus 5x. Right, so you can see that the degree here is 4. The number of turns here, the max of turns you should get is 3. This is also a positive even degree function because the a value, the leading coefficient, is basically 1, right? And the n behaviors would be found in quadrants 1 and quadrants 2. Okay, let's take a look at part E. Right, so in this case, the degree here, n is equal to 5. If n is equal to 5, this is basically a negative odd degree. It's a negative odd degree function. So if it's a negative odd degree function, then we can imagine that the n behaviors here should be in quadrants 2 and quadrants 4. Okay, so quadrants 2 and quadrants 4, and the number of turns you should expect are 4 in max, right? So in maximum you should only see 4 turns, and part F here we should see this is n is equal to 3. It's a cubic function, right? The n behaviors should be in quadrants 3 and quadrants 1, right? And this is basically a positive odd degree function. You should see a max of 2 turns. Excuse me. Okay, so let's figure out what each of these, so looking at all these characteristics, what are some potential sketches for each? Well, I'm going to start with part A here. We have 2 turns, n behaviors should be in quadrants 3 and 1. I think the best scenario for that would and it's a positive odd degree function, right? So I'd say this was B. Okay, so the best scenario for that, this is B. So that's off the chopping block, right? Okay, so the next thing we need to look at here is we also have so part B there is a degree of 4, there's 3 turns, and the n behavior is a negative even degree function, so both should be facing into negative infinity in part in quadrant 3 and 4. So I think the only scenario for that is part A. Okay, let's take a look at C here. It's n is equal to 2. There's 1 turn. It's a positive even degree function, so you should see it in quadrant 1 and 2. There should only be 1 turn, however. The only scenario in that case would be E, right? Because both of them are positive infinity and there's only 1 turn. Let's take a look at D here. There is 3 turns, n is equal to 4, positive even degree function, quadrants 1 and 2. Well, that's the only scenario for that is basically part C. Let's take a look at E here. This guy actually has 4 turns, and it's a negative odd degree function, quadrants 2 and 4. Well, the only scenario for that case is F, right? So this is F, and whoops. And then the last case here, this the only one left is basically D, right? So this was part F here. And in this case, you can see that it's basically positive odd degree function. And the way you can differentiate between D and B, right? You'd have to look at intercepts basically, right? So the only way to really look at it is through intercepts. But in this case, this would be D, because this would basically be odd, opposite n behaviors, and it looks like, there's 2 turns as well, right? So it is a little tough looking at these two. To be honest, I would probably go with, well, this is quadrants. We said this was, what did we say was B? Part A? Yeah, to be honest, I would probably go with, this is, I would probably switch these two, B and D, just because for A, this is the point is 0 and 2, and this is 0 and 1, right? So it looks like this was lower down than this guy, right? It's kind of hard to tell. You need a more refined sketch, right? So I would probably switch these two because of the y-intercept, right? So this would basically be D, and then this would be A, I believe, B. Okay, just because the y-intercept here is 0 and 1, and the y-intercept here was 0 and 2. Okay, but other than that, everything else will suffice. Okay, the final piece of the puzzle is we're going to be investigating the behavior of a function around a root, right? So root is also another name for an x-intercept, right? So roots are basically x-intercepts. And in this case, whoops, it's intercepts. And in this case, different x-intercepts can have different behaviors of the curve, all right? So let's consider an equation in factored form, and I'm going to look at 3 cases for you, okay? And if this is one of the factors of each x-intercept, of each function, sorry, okay, there's going to be some kind of power associated with each factor, okay? Now we can understand that, right, if this is part of a function, f of x is equal to, let's do x minus a times x minus b times x minus c, right? If it's some kind of function that includes x minus a, we know that a and 0 is one of the possible x-intercepts, because we know that an x-intercept will occur when y is equal to 0. So in this case, we would let f of x equal 0, okay? So we know we have an x-intercept for all these cases, and it's a and 0, but however, there's going to be different ways that the graph will behave around those x-intercepts, right? So when you have a power of a factor, right, this power is called the order or the multiplicity, okay? So the order or multiplicity is related to the power of each factor, power on a factor that can be used to determine a root, right? A root, or also known as an x-intercept. Okay? So a power of 1, you can say it's an order of 1, right? So the order is basically 1 in this case. And an order of 1 tells us that the graph, the behavior, right? The graph will pass through the x-intercept a and 0, right? So what that really means here is, this is our function. I'm just going to show you what an order of 1 will look like. Okay, so this is our graph, right? And let's say that this is our x-intercept, okay? So let's say this is a and 0, and if a graph passes through or slices through an order of 1, then it just looks like that. It can look like that, or it can go the other way around, right? It just goes through it, is what it's saying. Okay, and you can basically add to our notions of other aspects of behavior, right, that we looked at, like the end behavior and so forth. And this would help you to draw a much more a refined sketch, really, right? So we know that an order of 1 would mean that the graph will pass through a root, right, or slice through a root. If we have an order of 2, right, if we have an order of 2, that means that the power on the factor is 2, then what the graph is going to do here is the graph will bounce off or be concave to a and 0, okay? So I'm going to show you that. So this was an example of an order of 1 root, right? Or a multiplicity of 1. Let's take a look at multiplicity or an order of 2. Okay, let's say that this is our similar x-intercept. Okay, so this is a and 0. And if you bounce off an x-intercept, right, you could have a curve that looks like that, right? Or you can have a curve that looks like that. Okay, so this is what an order or multiplicity of 2 looks like. Okay, the third scenario, we can have an order of 3. So in this case, a graph will have a point of inflection. Right? The point of inflection is a change in concavity at x at a and 0, the x-intercept. Okay, so this is what an order of 3 looks like. Okay, so I'm just going to kind of construct that out. So I think you'll get a better picture of this, and I think the best way to kind of get a better picture of this is to do example questions. So really stay tuned in my further videos where I do show you guys examples of this stuff, right, and how it just kind of intertwines together, all right? But for the most part right now, I'm just kind of introducing this concept. Okay, so here is a point of inflection, okay? And the other case, okay, it can look like that. So you can see that it changes concavity, right? You're going concave up and then concave down and then concave up. Okay, so that's what a change in concavity is. In the other scenario, you can go concave up and then concave down, right? This is concave up, concave down. Okay, so that's what an order of 3 is. So these are essentially what we call orders or multiplicities. Right? It's really useful to understand what our behavior is around the roots, and you can tie this in with end behaviors and get a much more clearer picture of what your sketch will look like, right? We also mentioned earlier that, and I'm just going to add a page here, but we also mentioned earlier that you can also find extrema between the x-intercept, the midpoint of the two x-intercepts, right? So this is something I want to highlight, right? Like for instance, if this is your sketch of your graph, let's actually do a different sketch here. Well, sorry about that, guys. Okay, so if this is the sketch of your graph, okay, and you can notice here that this would be an even function because you have similar end behaviors. You have negative infinity and negative infinity, right? And you can find that the end behaviors are in quadrants 3 and quadrants 4, right? So this tells us that this is a negative even degree function. So it's a negative even degree function. And you can notice that if it's a negative even degree function, this guy has, looks like, 3 turns, right? I'm just going to highlight the turns in a different color. Right, there's a maximum here, there's a minimum here, and there's a maximum here, right? Because it's an even degree function, we have a restricted range, right? And this would represent an absolute maximum point, right? This would represent a local maximum point, right? So remember that for even degree polynomial functions, you will have an absolute maximum or minimum depending on if the a value is greater or less than 0, right? If a is greater than 0, we have an absolute minimum. If a is less than 0, we have an absolute maximum. Okay? And we can notice here that there are 3 turns, right? So this is a local minimum. And because there are 3 turns, we can notice that one of the turns can be determined by finding the y-intercept. Excuse me. But the other turns you can determine by finding your x-intercepts. Right, specifically the midpoint of your x-intercepts, right? So this is, we can notice that there's 4 x-intercepts here, right? And for all intensive purposes, right, we can say that this is x-intercept A, B, C, and D, right? And in this case, you can notice that for all of these factors, all of these factors should have a power of 1 because of the fact that the graph actually passes through them. It slices through these points, right? So it's really advantageous to look at functions in their factored form, right? So that's one of those things that we will kind of allude to later, right? That a polynomial function in factored form will give us a lot of information regarding its behavior, right? And it helps us to sketch it better, right? And we also noted that the midpoint of these x-intercepts represent turns, right? We can call this turn 1, we can call this turn 2, right? This guy's already given, so we don't have to worry about that, right? So the x value of turn 1 here is the midpoint of a and b divided by 2, right? And the x value of turn 2 here is b plus c divided by 2. So this is just a really quick way of determining or approximating where you would find your extrema. Now the best way is using calculus, right? But we're not, this is a separate course, right? You'll learn this further in different math courses that you will take in the future. And if you find the x value of the turn, you can just plug in to the function to find the y value, right? So this is basically your y value of your turn, b plus c over 2, right? So in conjunction with knowing behavior of each root, right, you can also figure out, but using the roots to find the points of extrema. So hopefully now you have all the tools that you need, but I think the best way to kind of understand this is by doing questions. So that's what we're going to be doing in the next upcoming videos. Which of the following graphs of polynomial functions corresponds to cubic polynomial equations with roots -2, 3, and 4? So in that sense, if we take a look at these functions, we can see that there is a series of roots, right? So we have -2, we have 3, we have 4 here. So this one would work, right? And a potential equation, because it just slices through the roots, right? Just a general equation for this family of function, we can write this as x plus 2x minus 3 and x minus 4. Okay, let's take a look at part B. So A would work, right? If we look at part B, we have an x-intercept at -3, -4, and also -5 and 2, right? So this definitely wouldn't work, right? But if I wanted to create an equation for part B, right, f of x could be equal to, this is like -1, -2, -3. Oh, this is -3, and then this is -4. Sorry about that. It's a small grid system, right? There's a 2 here, so here we have a times x plus 4, x plus 3, and x minus 2, right? And it passes through these points, so these are all powers of 1. Let's take a look at part C here. We have -2 here, we have 3, we have 4, right? And in this case, because it's concave to -2, I'm going to use a for the family of functions. We have x plus 2, but this time it's to a power of 2. And then we also have x minus 3 and x minus 4. So this also applies, right? So this is what a potential function could look like, right? And a is just, once again, it's the factor, and the x-intercepts are going to be the same for all of the functions in the family of functions. And part D here, because it has 3 roots, this is a quadratic, it can't have 3 roots, right? So in that sense, we know this wouldn't work, but we can still create an equation for this nevertheless, right? So in this case, this is f of x is equal to x plus 2 times x minus 3. Okay, so those are our 2 cases, but it's really important to understand that the order of the function can be a really useful tool in sketching out, or just even pinpointing a sketch of a certain polynomial function. All right, let's match each equation with the most suitable graph. Explain your reasoning. Right, so part A, we have f of x is equal to 2x plus 1 squared and x minus 3. Now here we actually, in order to match the sketches, we need to actually look at the order or the multiplicity of each root, right? So if we look at part A, I'm just going to write some of the characteristics down, right? The roots here, you can find the roots by letting f of x equal 0. So if I let f of x equal 0, I get 2 times x plus 1 squared. X minus 3 is equal to 0, and it's just as simple to solve for the roots. It's just as simple as letting each factor equal 0. Like I let x plus 1 equal 0, x is equal to -1, so -1 and 0 is one of my roots. The other root here is x minus 3 equals 0, x is equal to 3, so 3 and 0 is another one of my roots. Now you can notice here that the degree on your first root, or the order on your root here, right, is -1 and 0. The order here is basically 2, right? And because the order is 2, the behavior of this is going to be concave to -1 and 0. Okay? And the order at 3 and 0 here should be 1, because you can see a 1 there, right? And that means that it will slice, or it'll pass through. So it'll slice through 3 and 0. Okay? So something that's concave to -1 and 0 and that slices through 3 and 0, the only scenario that would work out would be part C. Okay, so we already looked at part C. All right, let's take a look at part B here. Right, you do the same technique. So the roots here, order, behavior. Okay, so the roots here for part B is negative 1 and 0 as well, and 3 and 0. Negative 1 and 0 we have an order of 2, 3 and 0 we also have an order of 2, and basically it's concave to these points. So a scenario where it's concave to both points would be part A, right? So A would be the only scenario where that actually works, right? So this is A, right? So we said that this is C, this is A. Let's take a look at part C, right? So I'm just gonna show you, you know what, I could probably fit some space here. If you're looking at part C, right, let's look at roots, order, the behavior. Okay, so in part C, the roots here are negative 1 and 0. Right, and the other root here is 3 and 0, and you can see that the order here for negative 1 and 0, for x plus 1, it's power 1. So it just basically slices through, or passes through. Right, I like using slices through, it's easy to remember. And then 3 and 0 here, the order here is 2, so it basically is concave to this point. So it's concave to 3 and 0, but slices through negative 1 and 0. Well, the only case that actually works out is B, right? So basically this guy. Right? And by default, D is going to be basically part D, right? And you can notice that the roots on part D here, right, I'm just going to use a different color, but the roots are, if you let f of x equal 0, you get 0, negative 1, 3, and 5, right? And the order for all of these, order of all factors are 1. So if the order of all factors are 1, it basically slices or passes through each root, right? And the only case where it does that is going to be D. Good? So this is going to be D. So it's going to go CA, B, D. Okay, let's create a function for the following. Okay, the first thing we want to look at here, well, we can notice that there is similar end behaviors. So this tells us this is an even degree function. Okay, we have similar end behaviors, and we can notice that we have a few x-intercepts. There's an x-intercept here, 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 and here, right? And passes through each x-intercept, so the order is 1, right? And we can also notice a couple of turns here. Okay, there's a turn here, and turn here. So this indicates that we have 3 turns, right? There's an even degree function, and we know that the degree should be turns plus 1, so the degree should be 4, right? It's an even degree function. The end behaviors are found in quadrants 1 and quadrants 2, right? So the end behaviors here are in quadrants 1 and quadrants 2. So this is consistent. All of this is telling us this is consistent with the positive even degree function. Now first I'm going to create the equation for the family of functions, and I'm going to plug in a point to determine to figure out what that function is specifically. Now in this case, for the family of functions, f of x, because the order of this function is going to be 1 for each of those factors, our x-intercepts here are going to be a x minus r, x minus s, x minus t, and x minus, let's do u, okay? And in this case, r can be 0, s can be 1, right? T can be 2, and u can be 4. Okay, so the potential equation for this function can be x times x minus 1 times x minus 2 times x minus 4. Okay, so now that we have that figured out, the next thing we want to do here is let's see if we can find this a value. Now we know that f of 0 is equal to 0. Well, f of 0 is equal to, if this is 0, then a is basically, oh, a is going to be 0. That's weird, right? So if a is 0, then we know that this a value is not going to be consistent, right? So we can just say that a is 1 or a is 2, but there's no other point that we can have here to figure this out. Okay, so we'll just stick with a as being 1. So it doesn't really seem like we have any other points, okay? So it's fine if we stick with the family of functions. right? Because once again, we don't really have too much of a refined sketch because I don't have this graph on grid paper, so that's fine. We'll let a equal 1, and technically your equation can be f of x is equal to x times x minus 1 times x minus 2 times x minus 4. Okay, and that is your function. Alright, let's create a function to represent the following graph. So by looking at this graph, you can see, first of all, there is opposite end behavior. This is positive infinity, negative infinity, and furthermore, this is extending from quadrant 3 to quadrant 1. This indicates that we do have a positive odd degree function. Now, we know this is a positive odd degree function. We can figure out what the degree is by figuring out the number of terns. Right, there's a turn. Well, we'll use a different color for that. Can't really see it. So there's a turn here, right? There's a turn here, right? There seems like there's a point of inflection here. Okay, so points of inflection count as 2 turns, guys. Right? So that's the one thing that you want to kind of understand. So because of that, we should actually have 4 turns here. We have 4 turns, and we know that turns are n minus 1. So then the turns are, whoops, the degree here is basically turns plus 1, so the degree here should be 5. So this is a quintic function. Could be potentially a quintic function, right? And let's take a look at some of the roots here. So if we're looking at our roots, let's look at the order and let's take a look at the behavior of the roots. Okay, so the roots negative 2 and 0, we can see that the order looks like 2 because it's concave to that point, right? And as a result, we should have a power of 2 there, okay, on the factor. Now we also have another root at 1, 0, but this looks like a point of inflection, so this actually has an order of 3, right? And as a result, our equation, f of x, should be in the form of a x plus 2 squared and x minus 1, sorry. I was looking at the 3 there. The root here is x minus 1 cubed. Okay? Now all we have to do, so this is the family of functions that will satisfy this equation, but now all we have to do is we need to plot a point to solve for this a value. Now, luckily we do have the point 0 and negative 2 on the graph, which is indicated there. So I'm going to do f of 0 should give me negative 2. So if I plug in f of 0 into my function, I get 0 plus 2 squared, 0 minus 1 cubed, and that's going to give me a times 2 squared, negative 1 cubed, which is basically negative 4a. Okay, so f of 0 is negative 4a, which is equal to negative 2. So negative 4a is equal to negative 2. If I divide this by negative 4, a is equal to 1/2. Okay, so if a is equal to 1/2, then our equation here, f of x is equal to 1/2 x plus 2 squared times x minus 1 cubed. Okay, so this is a potential function for our graph. Okay, determine the cubic function as zeros at negative 2, 3, and 4, and if f of 5 is 28. Well, if it's a cubic function, the degree is going to be 3, right? And we want to look at a cubic function in factor form. Now, if we're looking at a cubic function in factor form, we want to think about in the form of ax minus r, x minus s times x minus t, where r, s, and t are roots or x-intercepts. Now you can imagine here that these are all factors with an order of 1, right? That means it passes through these points, right? The total orders have to add up to 3. Does that make sense? So in this case, a potential way we can write this, ax plus 2, x minus 3, and x minus 4, right? So you just, you can let r equal negative 2, s equal 3, and t equal 4 if you plug it in. The only one that changes values here is the negative 2, because you'll have x minus minus 2 when you write it out, and then you get x plus 2. That's why you can think about it as changing the sign of it, if anything. Now, this equation represents the equation for the family of functions. Okay, so this is the equation of the family of functions, and a family of functions is basically a series of functions or polynomial functions that have the same degree and same x-intercepts, right? So same degree and same x-intercepts. The only thing that they really differ with is this a value, and a here is your vertical modification factor. Okay, your vertical modification factor can change, right? For instance, if a is greater than, first of all, if a is less than 0, there is a vertical reflection, right? So you can kind of recall this when you guys study transformations, right? When a is greater than 0 but less than 1, if a is a fraction, we have a vertical shrink, right? So a vertical reflection, first of all, means that, this is your original graph, right? Whoops. Wow. Sorry about that. Right, this is your original graph, right? Your reflection here is basically gonna look something like this. Right, but you'd have the same x-intercept. I didn't draw this too well, but I think you guys get the idea. Right, you get the same x-intercepts, and then this would be negative f of x, and then this would be f of x. Now, I didn't draw the cubic function in this scenario, I just drew a quartic function, but you get the idea. You would imply the same notion, right? A vertical shrink would mean that if this is your original function, and I'm just going to use a different function to show that, if this is a quadratic, this is your original function, right? A vertical shrink here would basically mean this, right? A f of x, and a here would be greater than 0 but less than 1. And notice I'm just looking at the absolute value of a, right? So that's what a vertical shrink would look like, right? And in the other scenario, if a is greater than 1, we have a vertical stretch. Okay, so I think I'll stick with using a quadratic to show you guys an example. But if this is, maybe I'll just do it out here. But if this is your quadratic function, f of x, the vertical stretch of that function would kind of look something like this. Right, you still have the same x-intercepts, but now it's the object, now the graph itself looks longer and narrower, right? So these are just some things to keep in mind. We want to figure out what this a value is, and we know that we're given a point, f of 5 is 28. Well, that tells us that 5 and 28 lies on the graph. Remember that f of 5 basically means y when x is 5. Okay, y when x is 5 is 28, so the point is 5 and 28. So what you want to do now is you want to plug this in, right, into your function. So if I do f of 5, you basically get a times 5 plus 2, 5 minus 3, 5 minus 4, which is a times 7 times 2 times 1, which is 14a. And we know f of 5 is equal to 28. So 14a is 28. And this tells us that 14a is 28. If I divide this by 14, a is equal to 2. Okay, so therefore, right, f of x, the equation here is 2x plus 2, x minus 3 times x minus 4. So that is your equation of your function.